Everyone out there in the live stream, welcome, welcome. Thank you for joining us. It's really great to have you here. So if you've got thoughts, comments you'd like to add to the show, please put them into the YouTube live chat, and we'll see what we can do to make that part of the show. All right, Julian, you ready to kick this off?
Yeah, sure.
Julian, welcome to Talk Python to me.
Thank you.
Yeah, it's great to have you here. And I think we've got a bunch of fun stuff to talk about. It's really interesting to think about how we go about building software at scale. And one of the things that I don't know how you feel about it. Reading your book, I feel like you must have some opinions on this. But when I go to a website that is clearly not a small little company, it's obviously a large company with money to put behind, professional developers and stuff. And you click on it and it takes 4 seconds for every page load. It's just like, how is it possible that you're building this software with so much? Oh, this is the face of your business. And sometimes they decide to fix it with front end frameworks. So then you get like a quick splash of like a box with a little UI, and then it says loading for 4 seconds, which to me feels no better. So I don't know. I feel like building scalable software is really important, and still people are getting it quite wrong quite often.
Yeah, I mean, I think it's all also because there's a lot of things what you want to do when you do that, which is like, well, I mean, write proper code for sure, but also you want to be able to meter everything, like to understand where the bottleneck might be. And that's not the easy part, like writing code and fixing bugs and stuff. And we all know to do that. But then if we are asking you to optimize, like, well, that's one of the things that I usually use as an example when I talk about profiling is like, well, if I were to ask you to more like, I want you to tell me which part of your code is using 20% of the CPU, you really don't know. Like you can guess, you can probably do a good guess most of the time, but for real, you don't know. You have no clue until you actually look at the data, use a profiler or any tool for that being that will give you this information.
Yeah, we're really bad in using our intuition for those things. I remember the most extreme example I ever had of this was I was working on this project that was doing huge amounts of math, wavelet decomposition, kind of like Fourier analysis, but I think kind of worse. And I thought, okay, this is too slow. It must be in all this complicated math area, and I don't understand the math very well, and I don't want to change it, but this it's got to be here, right? It's slow. And I put it into the profiler, and the thing that turned out was we were spending 80% of our time just doing finding the index of an element in a list.
Yeah, which is not insane. Yeah. My favorite, I think, programming quote is from Donald Knuth, which is early optimization is the root of all evil. Like it's widely known, but I mean, I think I will quote it every week or so now.
Yeah, it's fantastic. It's fantastic. Yeah. In my case, we switched it to a dictionary and it went 5 times faster. And that was it. Like, it was incredibly easy to fix, but understanding that was where the problem was, I would have never guessed. So yeah, it's hard to understand. And we're going to talk about finding these challenges and also some of the design patterns. You've written a really cool book called The Hacker's Guide to Scaling Python. And we're going to dive into some of the ideas you cover there. Also talk about some of your work at Datadog, where you're doing some of the profiling stuff, not necessarily for you internally, although I'm sure there's some, but it also could be, for so many people, like you guys basically have profiling as a service and runtime as a service, runtime analysis as a service, which is great. And we'll get into that. But before we do, let's start with your story. How did you get into programming in Python?
That's a good question. So actually, I think I started like 15 years ago or so. I actually started to learn Perl, the first programming language, like, kind of scripting language, like we used to call them, at least a few years ago. And yeah, I mean, I liked Perl, but I wanted to learn like object-oriented programming, and I never understood Perl object-oriented programming. Like their model was so weird for me. Maybe because I was young and I don't know, but and somebody talked to me about Python. I bought the book, like the ORE book about Python, and I kept it around for a year or so because I had no project at all, like no idea. Most of my job back then was to be a sysadmin, so not really anything to do with Python. And someday I was working on Debian, like the Linux distribution, and I was like, oh, I need to do something like a new project, and I'm going to do that with Python. And I started to learn Python this way with my project on one side, the book on the other side. I was like, that's amazing. I love it. And I never stopped doing Python after that.
That's fantastic. It feels like it very much was a automate the boring stuff type of introduction. Like there's these little problems and Bash is too small or too hard to make it solve those problems. What else could I use? And Python was a good fit for that.
Yeah, it's a great way. I mean, usually I have a lot of people coming to me over the years and being like, Julian, I want you to contribute to a project. I want to start something in Python. They're like, what should I do? And like, I don't know. Like, what's your problem you want to solve? Like, if you want to find a boring thing you want to automate or anything, that's the best idea you can have to. If it's an open source project that exists already, great. I mean, good for you. It's even better. But I mean, just write a script or whatever you want to start hacking and learning. That's the best way is to scratch your own itch.
Yeah, absolutely. It's so easy to think of, well, I want to build this great big thing, but we all have these little problems that need solving. And it's good to start small and practice small and build up. And yeah, I find it really valuable. People often ask me like, oh, I want to get started. What should I do? Should I build a website like this? Maybe a machine learning thing like that? I'm like, whoa. Like yes, you definitely want to get there. But if you're really, really just starting, like, don't kill yourself by trying to take on too much at once. So yeah, it sounds like it worked well for you. How about now? What are you doing day to day? I hinted at Datadog.
Yeah, so I've been doing Python for, I mean, the next 10 years after I learned Python, I've been working on OpenStack, which is a huge Python project, implementing a open cloud system where you can host your own AWS basically. And so everything is in Python there. So I work on very large, one of the largest, I think, Python project, which is OpenStack for a few years. And then I decided to go for a change. And Datadog was looking into building a profiling team, building a profiler, a continuous profiler, which means you would not profile your script on your laptop, but you would profile your application running on your production system for real. And I was like, that's not something I think anyone did before in Python, at least. So I want to do that. And that's what I started to do like 2 years ago.
That's really interesting because normally you have this quantum mechanics problem with profilers and debuggers, especially profilers like the line by line ones so much where it runs at one speed normally. And then you hit it with like C profile or something and it's 5 times slower or whatever it turns out to be. And you're like, whoa. This is a lot slower. Hopefully it gives you just a factor of slowness over it. Like if it says it spends 20% here and 40% there, hopefully it's still true in normal speed. But sometimes it really depends, right? Like if you're calling a function that goes out of your system and that's 20%, and then you're doing a really tight loop with lots of code, the profiler will introduce more overhead in your tight loop part than it will in the external system where it adds basically zero overhead. And so that's a big challenge of understanding profiling results in general. And it's a really big reason to not just run the profiler constantly in production.
Yeah,
right?
Exactly. It's I mean, and people do that now. I mean, if you have the right profiler, so the way C profile works, I mean, and we can dig a bit into that, but like C profile, the way it works, like it's going to intercept everything. It's what we call a deterministic profiler, where if you run the same program twice, you will get the same C profile output for sure. Like it's intercepting all the function calls that you have. So if you have a ton of function calls, it makes things like you were saying 5 times slower for sure, at least. So,
and it'll inject a little bits of bytecode at the beginning and end of every function, all sorts of stuff, and it actually changes what happens, right?
Yeah, exactly. So it can change the timing. It can change. I mean, it's a good solution to have a like ballpark estimate of what's going on, and it gives you pretty good result. And usually, it's a good tool. Like I used it a lot of times over the years, and it always gave me a good information. The problem with C profiles is that you can't use it in production because it's too slow. It's also not providing information, like it gives you the world time that you use, but not necessarily the CPU time of each of your thread, etc., that you're going to use. So the information is not really fine-grained. It's a rough.
Yeah, it's probably not streaming either, right? It probably runs and then gives you the answer, not some sort of real-time stream of what's happening.
So I mean, for one of the cases like we were mentioning previously, where I mean, this part of the code, like this scenario that you can recreate in a 1 minute script or something. It's slow and it should take only 30 seconds. You can run C Profile around it on 1 minute on your laptop and be, okay, I'm going to optimize this piece of code. Then if you want to see what's happening on production with a real workload for real, and like you were saying, streaming the data to see in real time what's going on, well, C Profile doesn't fit. And also, any deterministic profiler which tries to catch everything your program does will not work with good performance. So you have to do another approach, which is what most profilers for continuous profiling do, which is statistical profiling, where you actually sample your program and you try to look what it does most of the time and the most often. So it's not a true representation. It's not like the reality 100%. It's a good statistical approach of what your program is doing most of the time.
I see. Is that more the sampling style of profilers, where it's like every 200 milliseconds, like, what are you doing now? What are you doing now? What are you doing?
Exactly.
Like a really annoying young child, like, what are you doing now? What are you doing now?
Exactly.
And it's going to miss some things, right? If there's a function you call and it's really quick, it's like, well, you never called that function as far as the profiler is concerned because it just didn't line up. But if you do it enough over time, you'll get to see a good picture of, you don't care about the stuff that happens really fast, but you care about the stuff that happens really slow. And those are going to show up pretty largely in these sorts of
Exactly.
sampling.
So if you use C Profile, you will see this very small function call because it catches everything. But in reality, for the purpose of optimizing your program, you actually don't care. You don't care if you don't see them statistically, but because they're not important. So that's not what you want to optimize in the end. That's not where your problem lies, probably. It's in the like outliers, the one that you see often in your profile, the one you see like 80% of the time when the profiler asks your program, what are you doing? It's always the same function being called. That's the one you want to look at.
Yeah. So I think that fits quite well with the production style. I know I was going to ask you about your book, but we're sort of down in this profiling story.
That's fine.
And I've used Datadog's tools for error handling and like exception, let me know when there's an error type thing. So I have that set up on like TalkPython, the podcast site, and the TalkPython training courses site. And of course, when you turn it on, you get all these errors that are like happening in the site, but nobody's complained to you that you didn't realize there's some edge case or whatever. And it's really fantastic. But something I've never looked at is the real-time profiling stuff that you're working on these days. So maybe just, I have no idea what this is like. I can imagine maybe what it's like, but give me a sense of, what kind of stuff do I get out of it?
Sure. Yeah. So what you'll get, the first thing you'll get, it's two profiles. So you'll get flame charts, essentially, which are, these kind of charts where they look like flames usually because they are like orange and red and going up and down, and the height being the depth of your stack trace, and the width being the percent of time of resources that you use. So usually it's time you're going to meter. For example, we meter a wall time in CPU time. So what you'll see is if your function using a lot of wall time, is it waiting for something? Is it waiting for a socket to be read, for a lock to be acquired? But one of the other profile we gather is how much CPU is actually using. So if you want to know if your program is CPU bound, you will see which function is actually using the most CPU in your program.
Right. Because I could go to my hosting provider and I could check a box and say, no, I don't want to pay $20 a month. I want to pay $50 a month to make this go 2.5 times faster. If I'm CPU bound, that might actually work. But if I'm not, it probably has no effect or small effects, right? So knowing that would be really helpful. Can I scale this vertically, or do I have to change something else? Yeah.
It's the whole story around profiling, where most of our users, when they come to us, like, we save thousands of dollars because we actually understood that we got a bottleneck here or there, and we were able to downsize our deployment because we optimized this function, and we understood that this was blocked by this IO or whatever. And when you understand all of that with profiling, whatever the language is, by the way, being Python or Java or anything, you actually save a lot. We have terrific story about that, about customers or internal users saving thousands of dollars just because they were able to understand what's going on in their program, and scaling more. Scaling up was not the solution. Optimizing the right function was the solution. So yeah, you'll get CPU wall time, and we also do memory profiling. So you'll see all the memory allocations that are done by Python, which are kind of tied to the CPU usage, because the more objects you're going to allocate, and when allocate, even if they don't stay around, each time you want to create a new string, a new object or whatever, even for a few seconds, milliseconds, it costs you memory. Like you have to call malloc under the hood, you have to allocate memory, which takes time. So you will see that. So if you use a lot of objects that are not reused, for example, you might well want to see that. The latest one we shipped a few weeks ago is the heap profiler, where you actually see a sample of your heap, like the memory you use in real time, and what has been allocated on the heap. And like,
can you tell me what how many of each type of object I have? Like you've got 20 megs in lists, you've got 10 megs in strings. Okay.
No. I mean, in theory, yes. In practice, no. And I'm actually fighting upstream with the CPython folks to be able to do that. It's a limitation of CPython right now. Technically, I can't really do that, but I'm able to give you the line number of the file, the function name, and the thread that has allocated the memory. And I wish I could know the class name. That would be amazing. Like, for example, Java has that, and I want to add that in Python. So that will be my battle for next year. But I mean, and you will get, I mean, if you have a memory leak, for example, which is quite common, right, where you keep adding more objects on top of each other, and at some point your memory grows forever and you don't know where that comes from. With such a tool, heap profiler, you're able to see which stack trace is going to add more and more and more memory forever, and you'll be able to. No, it won't give you the solution to your problem. It will give you where to look at, which
it's
usually is
good.
It's like 90% of the problem. So yeah.
So can you talk a little bit about the internals of like how this works? I'm guessing it's not using cprofile
no
directly. Is it using other open source things to sort of put the service together, or is it all custom stuff you did?
No, it's custom stuff. Everything is open source, so we want to look at it. It's on our DDTrace repository on GitHub. So the way it works for the CPU and world-time profiler, it's pretty easy. And a lot of people know about that. You can actually ask CPython to give you the list of running threads. So if you do that 100 times per second, you get the list of running threads, and you can get the stack trace they're running, like the function name, line number that they're running. So if you do that a lot of time, you get a pretty good picture of what your program and threads are doing most of the time. So I mean, in summary, that's how it works. It's pretty easy. Then there's a few tricks to get the CPU time, etc., using the pthread API, but that's most of it. And for memory, they're actually a good thing that has been done by a friend, Victor Steiner, which is one of the.
He's done a great amount of performance improvement, like really important stuff. Yeah.
And one of the things he did in Python 3.4, so it was a long time ago, is to add this module trace malloc, which we don't use. I mean, I actually built on top of it at some point, but we don't use it anymore. We wrote a lightweight version of it, but it opened the memory API of CPython, where we can actually plug your own memory allocator to CPython, and that's what we do with our profiler. We replace the memory allocator by a tiny wrapper that catches every allocation and then do profiling on top of it.
Right, exactly. So when it says allocate this, you say record this was allocated and then allocate it, right? Something like that.
Yeah.
Is this the thing you were talking about on the screen, this ddtrace.py?
Yeah, exactly. You have a ddtrace directory, and inside there's the profiling directory, and all the code is there, so you can take a look at how it works internally. Yeah, I mean, the way we build it is to be able to be, easy to ship, to deploy. You don't require any extra permission. Like, there are a lot of different way of doing profiling using, for example, Linux capabilities, perf, a lot of things that are external and not necessarily portable outside Linux. But the problem is that most of the time they require extra permission, like being root or anything, like using the ptrace API requires you extra permission, which is great. I mean, there are great solutions, maybe better technically for some point compared to what we do there, but they are very complicated to deploy. So that was one of the things that drive us, I think, for writing this.
Right. So a simple pip install, plug in a line or two, and off you go, right?
Exactly. I mean, the setup is pretty simple. And so for exporting the data, we use the pprof format from Go, which is pretty standard. So you can actually use this profiler if you want, even if you're not a Datadog customer and you want to give it a try. You can actually export the data to a pprof file. and see what the data. You won't have the analytics that we provide and the fancy flame chart with all their rainbow colors, but you can use the pprof go tool, which is pretty okay.
Oh, interesting.
And
so you can get basically the raw data out of it just by using it directly. It's just you guys provide the
you have
nice
to store the
gathering.
file yourself.
Yeah, exactly. Yeah,
we provide the streamlining to our backend, and we provide ton of analysis. But if you are curious and want to take a look at how it works and what it can provide, I mean, it's a good way to do it too.
All right, awesome. I do want to dig into your profile, your scaling book, which is what we're going to spend a lot of time on. One final question though: can I diff profiles like from one version to another? Because one of the things that drives me crazy is, right, I've done a bunch of recording, I got my numbers, and then I'm going to make a change. Is it better or is it worse? What has gotten better? What has gotten worse? Like, is there a way to say compare?
Yeah, that's something we are building at Datadog on our backend side to be able to track your releases and tell you, well, this is going faster, this is going slower, and which functions or method are being the culprit, like of your slowness or whatever. So yeah, I mean, that's definitely something we want to do. Yeah,
that'd be so neat, because you know, you get it into you do maybe take a whole week or two and you sit down and you make your code fast and you get it all polished. And then over time, it kind of degrades, right? As people add new stuff to it and they don't really necessarily do so thinking about performance. So it'd be cool to like, okay, here's how it's degraded and we can just focus our energy in making this part better again. I think that'd be great.
Yeah.
All right. Well, tell us about your book. I find it fascinating. I kind of gave it a bit of an introduction, the idea of scaling it, but official title is The Hacker's Guide to Scaling Python, and the subtitle is Build Apps That Scale to Billions. Billions of users, billions of requests, billions of whatever, I guess. But most apps don't do this, so I think a lot of people would be interested in hearing about it.
Right. I mean, most apps don't do this, but so many apps don't really need to do that. So that's not a problem. I wrote that book, I think, 4 years ago now, because I was working, like I said, on OpenStack, where I would actually try to scale the things to billions, where it would be running, like it would be apps running on thousands of nodes. And
right. And maybe any individual app is not scaling to that level, but you guys basically being the platform as a service, in aggregate, have a huge amount of load put on it, right?
Exactly.
Okay.
And which at that point, like when I started to write the book, a lot of people were flying outside Python, outside the Python realm, because while Python is slow, you can't do anything meaningful with Python, right? It's so slow, you have to switch to Go. And that was a lot of things.
That's the first thing you'd have to do. Is I understand is that Python is slow, so you have to switch to Go, right? I hear this all the time.
Exactly. So I confronted about that. In the OpenStack project, somebody rewrote one of the software of OpenStack in Go because it was faster, and was like, nope. I mean, the Python architecture you use is slow. That's why the program is slow. It's nothing related to Python, like, and there's no need to switch to Go. Like, I mean, it's not related to the language. It's that the architecture is different. So that's what kind of motivated me at the beginning to write that book, to be able to share everything I learned for the years before building OpenStack. I mean, part of it, and learning on what works and doesn't work at scale in Python, and to stop people switching to Go for bad reasons. There are good reasons to switch for Go for sure, but sometimes no.
Exactly. Not just because it's necessary. So, well, you know, another example of this is people switching to Node.js because it can handle more connections, right? And the reason it can handle more connections is because it's written in an asynchronous way, a non-blocking way. And so if you write blocking Python, it doesn't matter if you write blocking C, it's not going to take it as well as if you write non-blocking, Python, right? And so things like Async Io and those types, ASCII servers and whatnot, can automatically sort of put you back in the game compared to those systems that the magic in quotes, the magic of Node was they made you do that from the start. They're like, oh, you can't call synchronous functions. So the only way you do this is you write crazy callbacks until, better ways like with promises and futures, and then async in a way get into the language. But right. They forced people to go down this pattern that allowed for scale. And then you can say, oh, look, our apps scale really well. And it's just that I think a lot of times people start with the easy way, which makes a lot of sense in Python, but that's not necessarily the scalable way. So start one way, but as you identify these problems, maybe bring in some of the ideas of your book, right?
Yeah, totally. I mean, that's why like one of the first thing I like to say about that is like Python is not fast or slow. First, it's like you would say like English is slow or English is fast. Doesn't make any sense. You have people, I mean, speaking English very fast over notes. It's like Python, the language. When C Python is slow, okay, it's not the best VM out there. Actually, I think it's far from being the best VM out there. I mean, by VM, I mean virtual machine of the language. Like if you look at the state of the art of, I don't know, V8 for JavaScript or Graal or whatever for Java, or the JVM itself is pretty great nowadays. And I mean, if you look at all of that, Python, I mean, C Python is really looking bad, I think. But then it has other upside, which gives you a good, I mean, good things when you use Python, and a good reason to keep using Python and C Python in the end. So I think it's a trade-off, and people are not always, putting the right weight at the right place for doing that trade-off.
Yeah, I agree. One trade-off might be, you could write it in, let's say Rust or something, for example, make it go faster. But then you're giving up the ability for people to come with just a very partial understanding of Python itself and still being really productive, right? Like people don't come to Rust and Java with very partial understandings of it and be super productive. They just don't, right? You got to take in a big bite of that all the computer science ideas there. Whereas like Python can start so simple and clean. And I think that's part of the magic. But some of the patterns of that simple world don't always make sense, right? I do like that you pointed out that not everyone needs highly scalable apps, right? Yeah. Because it's really cool to hear, they're doing this thing with Instagram, right? Like Instagram turned off the garbage collector and now they're getting like better memory reuse across their web workers. And so maybe we should do that too. It's like, well, hold on now. How much are you spending on infrastructure? Can you afford just $20 more and not have to deal with this ever, right? I mean, they run their own version of C Python that's a fork where they turn off the garbage collector, right? Like, do you really need to go that far? So I kind of put that out there, just kind of a heads up for people before they dive in, because kind of like design patterns. Like I feel like when you learn some of this stuff, you're like, let's just put all of this into place, and then you can end up with a more complicated system that didn't really need all those put in together at once. And maybe like there's no app that actually incorporates every single idea that you've mentioned here. Just they're all good ideas in their context, but not necessarily. You wouldn't order everything on a menu and put it all on one plate and then try to eat it. Right?
No. Especially because if you start, like, for example, the first thing people do usually is like, you write a program. Okay, it's not fast enough. Let's not say it's slow. It's not fast enough for you. You're like, okay, I want to make it faster. So if you can parallelize things. You're like, okay, I could run this in parallel. You go, okay, I'm going to use threads. All right, that's easy. There's a threading API. There are the concurrent future API in Python. It's really easy to do, but it adds so much complexity to your program. You have to be sure it's really worth it, because you're entering the world of concurrency, and then you're entering, you have to use locks. You have to be sure that your program is not having side effects between threads at the bad time or anything. And it adds so much complexity. It's actually very hard to make this kind of program right and to make sure that it works. And there are so many new edge cases you're adding by adding concurrency, being threads or anything else, but you have to be sure it's worth it. And for a lot of people out there, it's really not worth it. Like you could have a pretty simple application with just one process or a couple of processes behind a unicorn or USG worker and be fine forever. But it doesn't make any sense to try to optimize. And like I was saying, like early optimization, the root of all evil. Don't do it. Like unless you are sure and you actually know why it's slow, you know where to optimize, which might be a good user for a profiler or not, depending on what you're trying to optimize. But make sure that you understand the trade-offs you are doing. I saw so many people rushing into threads or anything like that and writing code that is invalid and are going to crash in production because of race condition, etc. and they never thought about. And it takes them months, years to get things right again, because it's very complex, and writing like multi-threaded code is not something humans do very well. So if you can't afford to not do it, don't do it.
Well, I think, going back to the earlier discussion with profiling and stuff, either in production or just with C profiling, measure first, right? Because And then you know so much better what can be applied to solve that problem. Because if the slow thing is you're waiting on the database, well, you sure don't need more threads to worry about that, right? You might consider caching. That could be an option.
Yeah.
You might consider indexes to make the database faster. But you could really easily introduce lots of complexity into the system by applying the wrong fix and not really get a whole lot better.
Yeah.
So, yeah. All right. Let's talk about scaling. I think scaling is just the definition of scaling is really interesting, because a lot of people hear that like, I want an app that scales, or like, man, YouTube is so awesome. It scales to, a million requests a second or whatever. I want that. And then they have their app running and they click the link and it takes 3 seconds, or they run the function and it takes 3 seconds. Well, if that app scaled well, it would mean it could run in 3 seconds for 100 people as well as it could run in 3 seconds for one person. Like, that doesn't necessarily mean faster. So there's like this distinction I think people need to make between high performance, fast code, quickly responding, and then scaling, like it doesn't degrade as it takes on more users, right? Maybe you want to riff on that a little bit?
Yeah, there are 2 dimensions basically, which is like we were saying, one is more users, which is more in parallel, let's say, and one is faster, like having the page being loaded faster. So there are 2 different things. If you want to really optimize one particular use case, like page being loaded or whatever, it's really a good practice. I mean, you can't really scale that request, a web request on multiple nodes unless it's very complicated. But like to load a page or REST API or anything like that, usually you want to profile that part of the code to be sure you don't have a database.
Yeah, and that's a case where profiling locally with cprofile might actually be really good, right? Like, one request is actually quite slow. Like, you could learn a lot about that running that in a profiler, and adding the horizontal scalability stuff might actually make it a tiny bit slower for each individual request, but allow many more of them to happen. So you got to figure out which part you're working on, right?
Yeah, keeping in mind, like, if you cprofile on your laptop is going to be different by using cprofile on AWS or anything you run, because like your database is going to be different, the latency is going to be different. So it's hard to reproduce the same condition on your developer laptop that you have in production. You don't have the same system. So, I mean, it's really a good way, and it can do 80% of the job. But in some cases, it's great to have continuous profiling on your production system, and that gives you a good way to optimize your code and to make sure that this dimension of being faster is covered. Then the dimension of, well, let's scale to thousands of users and still have the 3-second load for everyone. Then that's another problem, and that's where you actually don't need a profiler, but you need a good architecture of your program and your code, and be able to spawn new process, new threads, new node, new anything that can process things in parallel for you, and decouple, like split your program in different parts, and having a good architecture. And there you can do that with Python, with any programming language. I mean, honestly, but you can do it also that with Python. There's no need to switch to any other language if you know what you're doing.
Right. It makes such an important difference there. All right, so let's go. I thought it'd be fun to go through a couple of the chapters of your books and just talk about some of the big ideas there. And the first, you kind of build your way up to larger systems, right? Like, you start out. We already talked about what is scaling, but the next one that you really focused on is, how do I scale to take full advantage of my current computer? Like, the one I'm recording on here is my Mac Mini M1. It has 4 cores. Over there, I have my sim racing setup. It has 16 cores. Let's suppose I'm running on that one. If I run my Python code over there and I create a bunch of threads and it does a bunch of Python things, there's a good chance it's using 1/16 of that CPU, right?
Yeah, exactly. It's I mean, people who start with Python, usually it's that issue. I mean, pretty soon, where you want to run multiple. I mean, you want to run multiple threads in parallel, for example, to make sure your code is faster, and then, which is a proper way. I mean, outside Python, it's a proper way to scale. Like, running a threads allows you to run another execution thread of your program in another CPU. I mean, and threads were not used that much 20 years ago, because every computer had only 1 core, right? I mean, your personal computer, it was a Pentium with only 1 core, and nobody cared about the threads. Now that everybody 16 cores in their pockets. It's like, whoa, we should do multiple threads, right? So
Exactly.
yeah, so I mean, and that's where you started like 10 years ago, seeing more and more people being interested into using threads in Python because, well, I mean, I'm doing this computation and I could do it twice to go faster, so I'm spawning on new threads and doing that. Except that if you do that in Python, it doesn't work very well because there's this global interpreter lock, the GIL, which actually makes sure that your Python code works nice on multiple threads. But every thread running Python code, executing bytecode, they have to acquire this lock and L2 it forever until they're finished or until they get interrupted, which means you can only have one thread in Python running at a time on the Python VM, and the other thread have to wait or do other stuff which are not Python related, which is what a lot of C extension like NumPy or other C extension you may be using are doing. They're releasing the GIL and doing things which are not Python, but still doing things that are useful for you. But in that case, they're able to release the GIL and let the rest of the Python program runs. But if your program is 100% Python, you don't use any kind of C extension, no native code, anything, then all your threads have this giant bottleneck, which is the GIL, which block every thread. So if you run, I think my record is like 1.6 cores with a ton of threads on the Python program. Like you can't really use. I never managed to use 2 cores with a Python. A single Python program and a lot of threads. It's very hard to get to that 2 cores being used. So when you have a 3264 cores machine that you rent or that you use, it's a pretty waste of resources.
Yeah. So this is super interesting, and people often see this as like Python doing a threading restriction. And what's really interesting is the GIL is really about protecting the memory allocation and cleanup, right? It's incrementing and decrementing that ref count, so you don't have to take a lock every time you touch an object or assign a variable, which would make it really slow. It'd be more scalable, but it would be slower even in the single use case, right?
Yeah, I've had experiences to do that. This is actually what you have in Java. They have this kind of monitor, I think they call it, where you have a lock per object, and it works well for them, but don't ask me the details. But for Python, there have been a few experiments to do that, and yeah, it makes the thing very, very slower, unfortunately. So it's not a good option to go that road. And I mean, there have been, if you look at the history of the GIL, there has been a project called the GILectomy a few years ago to remove the GIL. I mean, there have been plenty of experiments to try to get rid of that. In the end, the problem that if we ever do that at some point, it will break the language, and a lot of assumptions around the language, because like in Python, when you add an item to a list, it is thread safe by definition, because of the GIL for sure. But if we start by saying, well, each time you want to add an item to a list, you need to use a lock to do that. Either we do it implicitly, but it's very slow, or you do it explicitly as a programmer, then it's going to be very tedious for sure. And it's not going to be compatible with the Python we know right now, which is not a good option. So we're stuck.
Yeah. Well, there is. Have you been tracking the work on PEP.554 multiple sub-interpreters with
a little
that
bit.
Eric Snow has been doing?
Yeah, a little bit. Which
I think that offers some really interesting opportunities there.
Yeah, I think it's a different approach. But it's a mix, like it's a trade-off between the multi-threading and multiprocessing.
Yeah, it's like a blend, like a half and half of them. Yeah.
But I think it's the most promising thing we have right now, because I don't think the GIL is going to go away anytime soon, unless somebody really, take a giant project and do that. But there's nobody, unfortunately, outside. I mean, inside the Python community. Like there's no company trying to sponsor any kind of effort like that. A lot of the Python upstream stuff, from what I see, are run by people, willing to do that on their free time, and some are sponsored for sure or hired by company, but a lot of them are not. And then there are nobody like a giant big tech company trying to push something like that forward. So it's probably what's also not helping Python. So the multi-interpreter thing is probably the next best thing we'll get.
I think it is as well, because I just don't see the GIL going away unless we say we're going to give up reference counting. And if you give up reference counting and then you add like a JIT and you get that's a really different change. And if you think of all the trouble just changing strings from Python 2 to Python 3, Like this is the
Exactly.
next level,
Like,
right? It's crazy.
okay, we're not finished yet. I still have to maintain a lot of Python 2 code, to be honest. So I'm not ready
Yeah.
to do Python 4
I,
yet. So
I
yeah.
don't think we're ready for it either. So I think subinterpreters is interesting, and subinterpreters are interesting because they take the ways in which you sort of do multiprocessing, which does work for scaling out, right? You kind of
Yeah.
do message passing, and each process owns its own data structures and stuff like that. And it just says, well, you don't have to create processes to make that happen. So it's faster, basically.
Yeah, and I think one of the problems with multiprocessing is also serializing the data between the different process, which is always, I think Stack Overflow is filled with that. People complaining about unable to pickle the data between multiple processes, which is very tedious. So I hope that having the subinterpreter thing will solve part of that, not having to serialize everything. Also in terms of performance, in terms of usage for sure, but also in terms of performance, you don't have to serialize and serialize everything every time you want to pass something to a sub process with a very huge save.
So in danger of not making it all the way through the other topics, let me ask you just a couple other real quick questions or comments that you call out a couple of things. One, like the CPU scaling is a problem, except for when it's not. Like sometimes it's not a problem at all. And the example I'm thinking of, if I'm writing an API, if I'm writing a website, any of those things, the way that you host those is you go to a server, or you use a platform as a service which does this for you, and you run it in something like MicroWhiskey or GUnicorn or something. And what those do immediately is they say, well, we're not really going to run it in the main process. The main process is going to look at the other ones, and we're going to create 4 or 8 or 10 copies of your app running all at the same time, and we'll like send the requests off to these different processes. And then all of a sudden, hey, if you have less than 10 cores, you're scaling again.
Yeah, exactly. So that's why, I mean, threads are great for things like IO, etc. But if you don't really want to scale for CPU and cores, threads are not the right solution, and it's way better to use multiple processes. So either way, I mean, Unicorn, UWSG, very good solution for web apps, or there are alternatives to like, I mean, to that, but. Yeah, or a framework like Celery for doing JAX, for example, which is able out of the box to spawn multiple processes to handle all of your tasks on multiple CPUs. And usually won't use, I mean, if you don't use any kind of Async Io like framework or Tornado or anything like that, where you only do have one process running one task at a time, you can spawn multiple processes, even more processes than you have cores. If you have 16 cores, you can start, I don't know, 100 processes if you have enough memory for sure. But memory is really not a problem unless you're, depending on what you do for sure. But like for a REST API, it's really not a big problem. You're not using gigabytes of memory per process and per request. So it's fine spawning a lot of unicorn workers.
Yeah, it depends on that for sure. So 2 things that I ran across that were interesting in this chapter that you covered were futurist and Kotlin. I'm not sure how you say that second one.
Yeah.
But can you tell people about these 2 little helper library packages?
Yeah, Futurist is actually, it's a tiny wrapper around concurrent.futures that you might know in Python. The thing, it has a few things that are not there, like the ability to have statistics about your pool of threads or your pool of anything you use process, or which will give you a pretty good idea. A lot of applications out there, they're like, okay, I can scale on, I don't know, 32 threads, 64, and you have a setting usually to scale that, and you don't really know as a user or even as a developer how many threads you're supposed to start and to run to handle your workload. You're like just typing a number randomly and see if it works or not. And having statistics around that is pretty useful. There are also some features, if I remember correctly, where you can actually control the backlog. Like usually you have a pool of threads or processes or a pool of anything trying to handle your task. But the more you add, I mean, it can grow forever. So having the ability to control your backlog and say, okay, I have enough tasks in the queue. No, you have to do something like, I'm not going to take any more tasks. So that's the pattern you see a lot in queue system. Usually people, when they design a queue system, they design the queue system with like, there's a queue, I'm going to take things out of it and process them. And they don't think about controlling the size of the queue, so the queue can grow forever. which in theory is great, but in practice you don't have infinite resource to store the queue and then to process it.
Yeah.
So you want to be able to reject works.
Exactly. Yeah. One of the big complaints or criticisms, I guess I should say, is in these async systems that they don't provide back pressure. Right. A bunch of work comes into the front and it piles into Async Io, which then piles just massively on top of the database, and then the database dies. And there's no place further back before the dying of the database where it kind of slows down. And so this is something that would allow you to do that for threading and multiprocessing, right?
Yeah, exactly. And which is one of the other chapter of the book, which the title is Design for Failure, and you could write an entire book on that, which is when you write your application, usually you write something in a very optimistic way because you are in a good mood and you're like, everything's going to work, right? And reality
is
you
test with small data and a few clients, right?
Exactly. And the more you scale, like the more you add threads, the more you add processes, the more you add nodes on your network, you're going to use Kubernetes to spawn 100 of nodes and version of your application. And the more likely it is to fail, like somebody's going to unplug a cable somewhere. Anything can happen for sure. And you're not designing for that. Usually you're designing in a very optimistic way because most of the time it works. But when it doesn't, if you really want to go at scale, I mean, if you really want to go far and you want to work even in extreme condition, like when the weather is really rainy, it's a lot of work. So that's why I was saying at the beginning, like it's a trade-off to add even threads, because then you have to handle what happens when I can't start a new thread anymore because I don't know, my system is on, which is pretty rare nowadays. You have a lot of space for threads usually, but if you are on very limited resource system or whatever, like how do you handle that?
Yep, threads pre-allocate a lot of memory, like stack space and stuff.
Yeah.
Have you heard of Locus at locus.io? Have you seen this thing?
No, I don't think so.
Yeah. So speaking of back pressure and just knowing what your system can take, this thing is super, super cool. It's a Python load testing thing that allows you to even do distributed load. But what you do that's really interesting is you create a class in Python and you give it tasks, and then those tasks have URLs, and then you can say, well, this one I want 70% of the time the user's going to go there, and then they're going to go here, and then I want you to kind of delay to like they click around like maybe every 10 seconds or so. So randomly around that time, have them click around, and it's just a really good library or tool for people who are like, well, I didn't test it with enough users because I'm just me. But what is it actually like? Something like this would be a really good option, I think.
Yeah, that's a good, even to gather data for profiling after. That's a pretty good. If you're able to reproduce something that looks application. Yeah,
that's interesting.
Yeah,
I mean, because you want to profile a realistic scenario. So instead of hitting one person, you hit it with like 100, and then get the profiling results of that. Okay, that's a good idea.
Yeah, that's usually the good thing with continuous profiling, is that you're able to see for real what happens. But if you know to reproduce it, that's also a valuable option.
Yeah. Okay. Very interesting. All right. So CPU scaling is interesting. And then Python around 3.4.3.5 came out with this really interesting idea of Async Io, and especially async and await. That makes Async Io so much better to work with. And what's interesting is that has nothing to do with threading. Like that doesn't suffer any of the problems of almost the problems of like the GIL and so on, because it's all about waiting on things. And when you're waiting, usually you release the GIL.
Yeah. So so threads are a good solution for I/O when you can't actually use something like Async Io, because let's be honest. I mean, if using an old library which was designed 5 years ago, it's not designed to be async at all. So, well, I mean,
or you're using an old ORM, and the old ORM doesn't have an async version of it, and it's either rewrite it in a new one, or use the old non-async, right? Something like that. Then maybe threads. I don't know.
Yeah, usually, I mean, ORM, it's a good bad example in the sense that it's a good example technically, but usually the problem is the people writing bad queries.
Yeah, I know. Better queries than an index. I'll probably solve that most of the time.
Exactly. But in theory, you're right. Technically, it's a good example. And I mean, event loops like Async Io, it's magic, because like you were saying, it's like the node thing that brought that back to life, where it has been used and there for the last 40 years, I don't know. And it's like suddenly everybody's like, well, that's amazing, and that's all you would write anyway, any web servers for the last 30 years. But it's great. No, it's built in Python, so it's pretty easy to use, and it's a very, very well. I mean, I think it progressed a lot over the year. Like a couple of years ago, where everybody was using Flask or Django, which is still true, but there's a lot of better alternative in the sense that like Starlet, etc., that fast API that you can use to build an API or website
This
based
whole
on Async Io.
this whole Async Io world has really flourished since you wrote the book, hasn't it? Yeah.
When I wrote the book, I actually learned Async Io writing the book, and there was nothing. It was very like the main problem is like I want to use, I don't know, Redis or like you were saying, a database, and there's nothing. So
Yeah.
or it's very low level stuff, and you're like, it's not going to be able. Like, yeah, I can use it, but it's going to take me hours of work to get anything close to what I would do with the synchronous version. So nowadays, yeah, it's totally better. And actually do a lot of work with Async Io myself. I mean, everything's there for every thing doing socket IO, file IO. Everything is available. There are sometimes multiple versions of the same library because people don't agree on how to do Redis or whatever, which I mean gives you choice. So that's great, and it's a very, very good way to not use threads. So you still have the concurrency problem where you can have multiple tasks from Async Io running not at the same time in our space-time dimension, but like being static means pause, being resumed later. So you have to still take care, and you actually can use lock too in Async Io. But it's still a little less of a problem and issue with threads. And you're not going to use more than one CPU for sure. That's not designed to do that. But you will be able maybe more easily because you will have less overhead than with threads to be able to use 100% of your CPU. Like you will be able to max out your resource, your CPU resource. And then when you do that with one Python process, well, just start a new one using Celery, Unicorn, whatever, or Cotiledon you were mentioning, which is a good tool to do that, which is actually able to spawn multiple process and manage them for you, because usually that's the problem when you have a demand. You want to do a lot of work. Like the Celery model for Q is a pretty good example when you have multiple workers and each worker is its own thread doing things in the background. If you're not using a framework such as Celery, and Cotiledon is a good small library to do that, where you can implement a class and have each class being spawned as a process basically, and being managed by a master process like you would do with Whiskey or Unicorn, and managing the child, restarting them if they die, etc. So that's a lot of work to do. You can totally do that yourself, but Cotiledon does that for you out of the box. It is pretty neat.
Yeah, that's a cool way to create those sub processes and stuff. But yeah, I think Async Io is a lot of promise. It's coming along. It's really been growing. SQL Alchemy just released their 1.4 version, which actually, so SQL Alchemy now just in like a couple of weeks ago now supports await, session query of thing. Not exactly that syntax, but almost. They've slightly adjusted it, but very cool. All right. And then one of the things that you talked about with scaling that I agree on that is super important is statelessness. So if you want to, and I suspect going from 1 to 2 is harder than going from 2 to 10 in terms of scaling, right? As soon as you're like, okay, this is going to be in 2 places, that means it has to be stateless and it's communication, all right? All these things. If you're just putting stuff in memory and sharing the pointers and kind of storing a persistent memory session for somebody, well, then putting that in 2 places is really fraught.
Yeah, it's really the thing where I like to say that if you start using multiple processes, you're actually pretty ready to handle multiple nodes like over a network, because using multiple threads, you're always in the same program. So it's tempting to share the state of everything between your different threads, and then you have concurrency issue and you need lock, etc. But a lot of people go that road, being, I don't know, maybe a bit naive and saying, oh, that's easy, I don't have to leave my program. But if you are ready to go to the step where you actually okay to split your work into multiple processes, which might have to communicate between themselves for sure, and they can start by communicating over the same host, but then you just add networks in between the process, and you can scale to multiple nodes and over whatever number of nodes you want. Then the problem is to handle connectivity issue that you don't have if you run on a single host between process. Usually you don't have somebody unplugging the invisible cable. But if you're ready to handle all of that network failure, which will happen for sure, between your different processes, then you can scale pretty easily on different nodes. But as you were saying, it's like you have to switch your padding when you write your program, which is being as stateless as possible. Which is why I wrote an entire chapter on functional programming, because I love functional programming. I love Lisp, and I would do Lisp if it was more popular, but I have to do Python, so I'll do Python. It's great. It's a great Lisp. But and then functional programming gives you a pretty good way of writing code and give you a good mindset, I would say, to write code that avoids to do side effects, and that makes your program stateless most of the time, which make it very easy to scale.
Right. The more statelessness you can have, the easier it is going to scale, and you can get it down to a point. Well, maybe the state is now stored in a Redis server that's shared between them, or even in a database. Like a real common example is just put it in a database, right? So like on the training site that I have, people come in, the only piece of state that is shared is who is logged in. And when it comes back, it goes back to the database. It's okay, well, who is this person actually? Do they have a course? Can they access this course? Like all those things are asked every time. And my first impression of like writing code like that was like, well, if I have to query the database for every request to get back all the information about, whatever it is I care about for I'm tracking on this request, it's going to be so slow. Except for it's not really. It works really well, actually. And it definitely lets you scale better.
Yeah,
it's pretty interesting. Okay, so stateless programming, which means like functional programming. You want to just like call out that example of remove last item that you have on the screen here, that the first page of that book. I think it will give people a sense of what you're talking about.
Yeah, exactly. It's like I was trying to explain in that chapter what's a pure and non-pure function, where you actually have one function doing the a side effect. When you pass argument, like functional programming, if you never heard of it, is pretty simple. Imagine that all your functions are black boxes, and that you are going to put something in it, and when you get something out, you can't reuse the thing that you put inside. Like you're going to use only what's being output. So when you don't do a pure function and functional programming, you're going to pass a list, for example, and you're going to modify it and not returning anything, because you actually modified the list that you passed as an argument, which is not functional at all, because
maybe list.sort would be an example, right? Like the thing you're calling sort on is changing the list itself.
Yeah, which is and that's trade-off, because list.sort is usually faster than sorted, calling sorted on the list, but it's not functional. But if you call sorted, or if you return the list minus the last item, for a function that removes the last item, then it's functional. You're not returning the same list, you're returning a new list with a different output, like the last item being removed, but it is stateless. Like you can lose the first what you put as an input. You don't care anymore. You have something that is outside. And if you design all your program like that, it's pretty easy to imagine having a large input of data, putting that into a queue, then having a worker taking that, doing whatever they need to do, and then putting something and putting that into another queue, database, whatever you might want to do. And that's the basis of any thing that scales, is to be able to do that, to be able to scale and do asynchronous task in the background.
Cool. Yeah, I think list.sort versus sorted of list is like the perfect comparison there.
Yeah.
All right. You touched on queues, and I think queues have this possibility to just allow incredible scale, right? Instead of every request trying to answer the question or do the task it's meant to do entirely, all it has to do is start a task and say, hey, that started, off we go, and put it into something like RabbitMQ or Celery, Redis queue, something like that, and some other thing that's going to pull it out of there and get to it when it gets done, right?
Yeah, exactly. It really depends on what you do and what you're trying to store with your application, library, whatever. But as a general thing, it's a pretty good way and architecture of a program to have that. Like if you, for example, a REST API, which is what people do most of the time now, you can definitely process the request right away. And if you know that it's going to take, I don't know, less than 1 second, okay, it's fine. You can do that right away. But if you know it's going to take 10 seconds, 20 seconds, it's very, very impractical for a client to keep a connection open for 30 seconds for good and bad reasons. But
and almost anyone's going to think it's broken, even if it technically would have worked. Like, it's been 10 seconds and there's something wrong. This is not okay, right? Like it's just not the right response.
Yeah, and I mean, connection can be cut. So if you need 20 seconds to do anything, and then it is being cut at 18 seconds, then you lost your time, and the client has to retry. So it has to repose the same payload, and then you have to reprocess it for 20 seconds. So you are actually losing time. So it's way better to take the input, store it in a queue, reply with 200. Okay, I got the payload. I'm going to take care of it, and then I will notify you with the webhook. I'm going to give you the result at this address, whatever mechanism you can use to do asynchronous. But I mean, building this kind of system asynchronously when you have the worker taking message from the queue, processing them, putting the result somewhere else, it's sort of a really good way to scale your application. And you can start without, I mean, you can start with Python itself. Like there's a queue in Python. There's multi-process, and you don't have to like deploy RabbitMQ, whatever. You can actually start if you know
You
your
could
program
even just
is not.
have a background thread and a list.
Yeah, exactly. I mean, you can start with something very simple for this pattern. You don't have to use a huge framework or whatever. If you know the pattern and you know it applies to what you're doing, you actually can use it. And you know, for example, that you will never need more than, one host, one node, one computer will be enough forever for your program. While you don't need to deploy a network-based queue system like
Right.
Redis, Rabbit, or whatever. You can use Python itself, use a multi-process queue, and that will solve all your problem perfectly.
Yeah, that's a great example. And the multiprocessing has an actual queue data structure that it properly shares across with notifications and everything across these these multi-process processes, where the multi-process thing can just say, I'm going to block until I get something from the queue. And then as soon as you put it in, it picks it up and goes. But otherwise, it just chills in the background. Yeah, very nice. All right, moving on. Designing for failure. That's a good one. The thing that comes to mind is at the extreme end of this. When I talked about scalability, I maybe said YouTube and a million requests a second. This one is Chaos Monkey and Netflix.
Yeah, exactly. Yeah, you have to design for that. So, like I was saying, like a lot of people that try to write their code with a very optimistic mindset, like everything is going to be fine, and I don't really care about errors and exceptions. Where you actually want to write proper exceptions, like proper classes of exceptions and proper handling of this exception in your program, and making sure that when you, for example, when you use, I don't know, Redis and you use a Redis library, you want to be sure to be aware. And that's something that's not very obvious, honestly, because it's honestly not really well documented. Like you can read the API of a Redis library and see, okay, it takes that type as an argument and it's going to return that type, but you don't know which exception is going to be raised. So sometimes you have to, to see it with your own eyes in production, like, oh, it's broken, it's going to raise connection error. Okay, no, I know I need to fix it. But
well, the tricky part of that is not necessarily seeing the exception and knowing it, but now what? Like when I get the connection error, well, it means I can't talk to the database, it's overloaded, or it's rebooting because it's patching, but then what happens, right? Like, how do I not just go, well, there was an error, tell the Datadog people there was an error so we know, and then crash for the user? Like what do you do beyond that?
Yeah. And the answer is not obvious. It really depends on what you're doing. Like if you are in a REST API and your database connection is broken, you can connect to the database. I mean, what are you going to retry for? How much? I mean, how many times? For how many seconds are you going to retry? Because the other guy is waiting on the other side of the line, right? So you can't do that for 10 seconds. It's too long. So you have to do that a few times. Then what do? Do you return a 500 error and crash, or do you return something that is like a retry later? I mean, there's a lot of, and you have to think about all of that, like when to say to the client to retry, if they can retry, or just crash. That's also an option sometimes. But and there are so many patterns. Most of the time, network errors, but it might be disk full or whatever, and you have to. So you can't think about everything at the beginning for sure. So you have to have a good report system.
Are you a fan? I totally agree about the reporting system. It's hugely valuable, and notifications as well. Because if you don't look at the reporting system, the log is full of errors, and nobody would look for a week. But are you a fan of the retry decorators? You know what I'm talking about? Some of those things you can say, here's like an exponential back off. I like you to retry 5 times, and like first after like a second, and then 5 seconds, then 10 seconds. What do you think?
I'm the author of Tenacity, which is one of the
Okay.
most widely
Yeah,
used.
that's one. Yeah, okay. So that answers that question. You're a fan.
Exactly.
Okay, cool.
I am a fan, and it's all 80% of the problem. I mean, then it's up to you to know how to retry, but it's a very very good pattern to use, and I mean, Tenacity provides that as a decorator, which is not the best strategy if you want to have different strategy, or like this function should be retried this number of times depending on who the color is.
Yeah.
But most of the time it's good enough. Actually, it's good enough. Like most of the time it's better to use that in a naive way where you just retry 5 times for 5 seconds or whatever, but not doing anything. Because if you know, it's also not a silver bullet. Like I see sometimes people using it to like, well, if anything wrong happens, I'm just going to retry, which is not like, please use proper exception types, like catch the right thing and retry for the right reason, not for everything.
Right. Like maybe retry with connection timeout, but
yes, but like if
some other thing that crashes, like authorization failure, like that's never going to get better.
Exactly. But sometimes you see people writing like, well, I'm going to retry an exception. Whatever is raised, I'm going to retry, which is really not a good idea, because it's going to be fine for network errors, but like you were saying, if it's authentication, you don't want to retry. So I mean, be careful in that. But then if you know that you got an IO error most of the time because the network is down one day, it's fine to do that, and it's a really really good way to design. I mean, easily for this kind of thing. It doesn't solve everything, and for, I don't know, if you have a large job, for example, that you know is going to take 10 minutes to compute, etc. I mean, having there this kind of retries is going to save you. Because in a framework like Celery, for example, if your job fails after 5 minutes, for whatever reason, it's just going to put it back in the queue and retry later. But you lost the first minutes that you used.
And you can end up in these poison message scenarios where it tries, it fails, it goes back. It tries, it fails, it goes back. It tries, and then that's not so great. All right, just a little bit of time for some more deployment. You talk about in your book, you talk about deploying on a platform as a service, a PaaS like Heroku. There's always VMs. These days we have Docker and Kubernetes. I mean, honestly, it's not simple to know what to do as somebody who is a newcomer, I think.
Yeah, and I think it changed a lot since I wrote the book, but nowadays Heroku is still there and pretty widely used because it's a good solution. The thing is that deploying a Python application, like for myself, I'm a pretty good Python programmer, but then outside of Python, like infrastructure and Kubernetes, I barely know anything about it. It's like, it's a full-time job and it's not my job. It's another side of another job. So I could learn for sure, and I could be an expert in Kubernetes and deployment of anything, but I mean, and it's fine to do that if you want to do that, but as a Python developer, I don't really want to do that. And I'm happy to use any kind of platform as a service like Heroku, where I can actually, like the using the Kubernetes container approach of deploying and spawning a lot of this to scale is not my responsibility, but I can, outsource it to somebody that knows how to do that. So there's plenty of options. I think I wrote about Heroku. OpenShift does that too. I mean, Amazon or Microsoft or Google, all other solutions
they
do
must
that
have
too.
something,
Yeah, and I mean, nowadays there's no reason, if you really know that your application is going to scale and you don't want to spend a lot of time on infrastructure and learning, I mean, Kubernetes, Docker, or whatever. I mean, you can spin easily an application on top of Heroku, and then click a button to have 2 nodes, 3 nodes, 4 nodes, 10 nodes, and then when it's expensive, but that's another issue.
Yeah, the platform as a service, often they exchange complete ease of use with maybe 2 things. One with cost, and then the other is with flexibility, right? Like you kind of got to fit their way. Like, well, the way you use the database, you use our managed database service. And if you don't like that, well, then I don't know, you got to just use our managed service. You know what I mean? Things like that are kind of somewhat fixed, but I think it's really good for a lot of people.
Yeah, exactly. I mean, it covers 90% of the market, right? I mean, most people that are going to start with, even if it's not a bad project, but like you're starting your company, you're doing a small project, and maybe it's one day you will be the next Google, you have to scale. But at that time, you'll solve the problem. You'll get plenty of money to solve it. But until then,
Yeah.
you don't have a lot of time. You don't have a lot of money. It's actually pretty cheap compared to the time you will spend learning the ropes of Kubernetes. I mean, a secure deployment at scale of Kubernetes, I'm sure it's pretty more complicated than writing a simple Flask application. So it's a trade-off. I think it's a pretty good trade-off if you really want to start saying, okay, I think at some point I will need to scale. I can't run on my laptop anymore. I need to run that somewhere. While using a platform like that is a pretty good trade-off.
Yeah, and I think it's so easy to dream big and think, oh, I'm going to have to scale. Like, so if I'm going to deploy this, what is it going to be like if I get the first 100,000 users? You should be so lucky that you have that problem, right? Like so
Exactly.
often things get built and they just stagnate or they don't go anywhere. Or the reason they stagnate is you're not adding features fast enough because you spent so much time building complicated architectures for a case in the future, when reality is on the past, you could just pay 10 times as much for 2 weeks and then completely move to something else. And you could buy yourself that time for $500. Right. But you could spend months building something, right? Like that's going to support some insane future that doesn't exist. And so, you know, a lot of people, they'd be better off to just move forward and then evolve and realize it's not forever. It's a path towards where you're going to be.
Yeah. And then learn marketing to have people coming
Exactly.
onto a project.
That is the problem. Yes, that's
that might be my next book about like doing marketing to getting people on your project to be able to scale them.
Yeah, I'll definitely read that book if you write it. All right, we got some more topics to cover, but we're down to just one that I think we have a little time to touch on because it's like magic sauce. For database, the magic sauce is indexes. For many other things, the magic sauce is caching, right? If this thing is really slow, I'll give you an example from TalkPython. We have, or maybe even better from Python Bytes. That's a more interesting example. Is that RSS feed for that thing is made up out of, I think we had to limit it because we got too many, but for a while it's made up of 200 episodes. Each episode is like 5 pages of markdown. In order to render that RSS feed on demand, I've got to go to the database, query 200 things, and then markdownify them 200 times, and then put that into an XML document and return that. And that is not super fast. But you know what? If I take that result I would have returned and save it in the database and just generate it once a minute, then it's fine, right? It's like magic. It goes from 1 second to 1 millisecond, and you just get so much scale from it.
Yeah, that's exactly what you're saying. Like it's a pretty good pattern when you have to optimize. So that would be more for the like performance dimension when you want your code to be faster, not necessarily to scale in number of users. Even if that's sometimes connected, like if you have 200 people requesting at the same time, your RSS feed and you have to do that at the same time 200 times, that's pretty useless. So I mean, caching is a pretty good pattern. There's nothing actually very specific to Python there. I mean, even in this chapter of the book, it's actually pretty like I'm talking about how to use memcache or Redis or whatever you want to cache. There are plenty of good solution to cache over the network. You can start by caching locally in your own process, like
just create a dictionary, like a Python dictionary is a really good cache, right? For certain things.
And there are in Python 3 something they added the LRU cache.
Yeah, the LRU cache decorator is really neat.
Cache tools, the cache tools library in Python. There's a lot of different algorithms if you want to cache locally in your own Python program. Like if you know you're going to call this method 100 of times and the result is going to be the same, just cache it. If it's expensive to compute, I mean, expensive to compute might be expensive in terms of CPU, but it also might be like expensive for database, or sometimes the expensiveness is going to be the network. Like you're going to request some data over the network and it's very far, or it's a very slow system or very unreliable system. So using caching system is a pretty good solution to avoid this kind of, which is also linked to the design for failure we talked before.
Right. If you're consuming third-party services, you can't necessarily depend on their uptime, on their reliability, on their response time, all those types of things. I'll give you another example of expensive. So when you go to our courses, we've got 12 video servers throughout the world, and we want to serve you the video from the one closest to you. So we have a service that we call that takes your IP address, figures out where you are, and then chooses a a video server for you, so you get the best time. That costs a little tiny bit of money each time, but with enough requests, it would be hundreds, maybe even, I don't know, definitely into the hundreds per month of where is this person API charges. And so we just cache that. Like if this IP address is from this city or this country, we just put that in our database. And first we check the database. Do we know where this IP address is? No, go to the service. Otherwise, just get it from the database. It's both faster and it literally doesn't cost as much. It's less expensive in the most direct meaning of that. Yeah.
And then you're eating on the first and biggest issue in computer science, which is cache invalidation, which is, well, in your case, the IP might not change of country.
It can change, not very often, but it can change. Yeah. So for our example, what I did is it's in MongoDB. So I set up an index that will remove it from the database after 6 months.
Yeah, which is fine, but arbitrary, right?
Yes, it's totally. I could be wrong for a while. I mean,
exactly.
But the failure case is it's slow streaming with buffering potentially. It's not complete failure or completely the wrong answer, right? So for us, it's acceptable.
Exactly. So you made a trade-off, which is totally fine for your use case, and that's a lot of things that you do when you want to scale is trade-off, and sometimes you don't get things totally right, but it's fine. It's just not the best experience for your user in your case, but it's fine and you can live with it. And I think it's a change of mindset when you go from I'm writing a Python program which has to be perfect and works 100% of the time, and then when you want to scale, you have to do a lot of trade-off where like it will work fine for 80% of the people, and for some cases 5% of the time, while that might be not optimal, but it's fine. And that's a lot of doing things at scale are changing this mindset to, well, it works always, it's always true, and no, sometimes it's not really true. I mean, if you had a way for you to be aware and notified that an IP address changed its country, you could invalidate your cache and then make it totally reliable. I mean, for a few seconds, maybe it won't be up to date, but that would be close to perfection. Yeah, but you don't have that system, so you have to do what you did, which is a good trade-off. I mean, it's pragmatic. You have to be very pragmatic when you do things at scale.
Yeah, and also kind of designed for failure. Like, what's the worst case if that goes wrong?
Yeah,
right. It's like streaming halfway around the world or something. Whereas other things, like if the database goes down, you got to deal with that entirely differently.
Yeah,
it's a hard one to fix, though. I don't really know what to do there.
Well, I mean, caching, like you could cache, for example, if you
that's true.
Down, you could cache an older version and reply to the client like it might be an older version. I'm sorry, like what the time is there, or I mean, depending on what you build. Obviously, you have to know the use case and the trade-offs you're going to do, but caching could be a solution. And then
that's a good idea, because you might actually be able to say, if I'm going to go to Redis, and if it's not there, then I'm going to go to the database. Many of the requests that come in might never need to go to the database again. If you just say, oh, whoops, the database is down, we're just going to serve what's out of the cache. It could go for a while until there's some write operation. Like, as long as it's read-only, it might not matter.
Which is what services like Cloudflare does for the web, for example. Like they do caching that protect you, and if you're down, they're just going to show the page they had a few seconds ago until you're back up, and nobody will notice. So
yeah, interesting.
You can apply that. Yeah, you can apply that, and the thing you have to keep in mind when you do caching is to be able to invalidate your cache. Like if you're caching database and something changed in the database, you have to have this callback mechanism where your database can say to your cache, hey, by the way, that changed, you need to update it. If you're able to, you need to be aware of that. Otherwise, you have to put arbitrary timestamp, like you said, for your 6 months. It's going to be 6 months, and that's it, which is fine for such a use case. But for a lot of your like your RSS feed, that wouldn't work very well probably if you were doing 6 months.
Yeah, that would be bad. All of a sudden, there's 24 new episodes all of a sudden or something. Yeah. So this is where you write that cron job that just restarts Redis once an hour and you'll be fine. No, just kidding. You're right. Like this cache invalidation really, really is tricky, because if you check the database, then you're not really caching anymore. Right. You might as well not have the cache. So yeah, it's super tricky, but definitely a bit of the magic sauce. All right. I think that there's plenty more we could cover in the book and about scaling and architecture, and it'll be really fun, but we're way over time. So we should probably just wrap it up with the couple of questions here that I always ask at the end of the show. So Julian, if you're going to write some Python code, what editor do you use?
Emacs. I've been an Emacs user for the last 10 years. I think I still have the commit access to Emacs itself. So
Oh, cool. You did say you love Lisp and you get to
yeah,
have your code powered by Lisp.
exactly. Yeah, I wrote a lot of. I stopped, but I wrote a lot of Lisp like 10 years ago.
Yeah, cool. The notable PyPI package, if you want, you can shout out Tenacity, which we covered, or something else if you like.
Tenacity and diequery, which I love. Diequery is a tiny wrapper around the logging system of Python. So the story is that I never remember how to configure the logging system in Python. Like I do import logging and I'm like, I don't know how to configure it to work like I want. So diequery does that. It's pretty easy to use. It has a functional approach like Tenacity in its design, and it's making like 2 lines to use the logging system. You have something that works out of the box with colors, etc. So
Oh,
like
fantastic. Yeah, I always forget how to set up the logging system and use something else as well. It's just like I don't need to remember this. Fantastic. All right, so thank you for being here. Thank you for talking about this and covering all these ideas. They're fascinating, and they always require some trade-offs, right? Like it's a win. Should I use this thing or that thing? But people want to get started. 1, where do they find your book? 2, what advice in general do you have for them in going down this path?
I think, you can find my book, scalingpython.com, if you want to take a look. It's a pretty good read, I think, to give you the right mindset to understand what the trade-offs you might need to do in your program. And I think that boils down to that, like, what are you ready to change and how to design your program, and what is going to be your real use case? Like, why do you want to scale? And are you going to scale for real, or are you just thinking that you will need to scale in the future? And do the right trade-off, and don't overcomplicate things, because you're just going to shoot yourself in the foot by doing that.
Yeah, it's super tricky. I would just add on to that. If what you think you might need to scale in the future is a web app or web API, use Locust to actually measure it. And if what it is something more local, like a data science type of thing or something computationally locally, run cProfile with it and just measure, right? However you go about your measuring.
Yep.
Yeah. Fantastic. All right. Thank you, Julian. It's been great to chat with you and sharing these ideas. Great book.
Thank you, Michael.
Yep. Bye. And bye, everyone out there in the live stream. Thanks for being